Welcome back, Hyperbolic Coding Chamber Extravaganza Supreme. It is day 37. Another day, another chance to test ourselves against the litmus test of men and women in the LeetCoding Coliseum. Years and decades and centuries ago, they would battle for hours. Now we battle for hours against computers. And I'm going to be honest, it's a losing battle because we got fried by coin change. I think that was yesterday. Oh, no. We fried coin change yesterday. And course schedule, this problem fried us yesterday as well. So definitely need to redo this one. But we're back once again, and we have 3 problems lined up from the grind 75, product of array, validate binary search tree, and rotting oranges. So I want to see if we can handle these problems. Additionally, reflections on the grind so far. About 37 days in, and I'm really hoping by day 100. We've really done a lot of problems by then. So that would be pretty dope. I think things are slowly speeding up. They say if you want to go fast, go slower. So that's what we're trying to do. That being said, maybe there is a faster way to go slower, right? Got to be a good question to ask. There got to be some good answers as well. But yeah, we're checking through a lot of problems. Validate binary search tree, rotting oranges. I don't think I've tried this problem before. That being said, though, the remaining number in the grind 75, there's still a lot left. We've only pretty much done, we haven't even done half of the problems. Maybe in 6 problems we'll have done half of the problems. But good problem set. I don't even know what problems I've done. But most of them seem to be easies and mediums. Now we seem to be in the medium era. So I wish they could tell you how much you solved or what denominations you've solved problems within. But that seems to be not be the case. But yeah, make sure to join the Discord, the Hyperbolic Coding Chamber. Thousands upon thousands of people are joining every day. It is pretty hype. It's pretty exciting. And honestly, there's a lot of secret tips in there. Additionally, if you're doing something similar, or if you're working on like other problems or just LeetCode for fun, drop me a tip, drop me an insult, drop me some constructive criticism. And yeah, if I mess up on the time complexity or anything like that, feel free to drop a comment about that, or if something could be done better. I'm also still recovering from a bit of sickness, so brain's a bit foggy there. I'm going to keep it $1.50. But I think I took my temperature earlier, and it's like 101 degrees, which means we just have to solve 101 more problems, and our issue should be resolved mentally and physically. So I'm just going to jump into product of array except self, but I have to load the timer first. So our timer has returned, and we're going to do the standard. Probably do a standard 2 hours here. See what we can get into. So we have day 37, and we're starting with product of array except self. So given an integer array nums, return an array answer such that answer sub I, given an integer array nums, return an array answer, okay, such that answer sub I is equal to the product of all the elements of nums except num sub I. So it doesn't sound too bad. The product of any prefix or sum of nums is guaranteed to fit in a 32-bit integer. So that is good. You must write an algorithm that runs in linear time and without using the division operation. So given an integer array nums, we have to return an array answer such that answer sub I is equal to the product of all the elements of nums except num sub I. So 1 is equal to the product of 2, 3, and 4, right? And 12 is equal to the product of 1 times 3 times 4, and 8 is equal to the product of 1 times 2 times 3. So this is actually interesting. So we know our output array is going to be the same length as our input array. So maybe we could perform this with we have to write an algorithm that runs in linear time, so we probably should be able to do this in multiple passes of n, right? That at least should be less than n, right? So if we can imagine that, right, what if we were to iterate through the array and store the values, right? So if we're iterating through the array, right, for index I, right, we would do 1 times 1, right, and then we go to index 2, right, maybe we want to store 2 in 1, right, and then if we go to index 3, right, maybe we want to store right, so I'm thinking what we can actually do, maybe we have an output array that's already created, right, and maybe the values in it are set to so our nums array can have 0, so I was going to say maybe we could set our starting value to 1. That looks troublesome. So what if we have an output array, right? So this output array would start with the let's just say all zeros, right? Input array is 4 and output array also has 4 in elements. So if we iterate, right, we're at index 1, we're going to want to multiply pretty much everything. We're going to want to go iterate through every array, through every element, right, and set it equal to 1. Now if we do that, that would actually be n that actually be n squared, so we can't do something like that. So maybe what if we did a carrying thing? So what if we said we start at index 1, right, we go to 2, I would do 1 times 2, right, 1 times 2, and then you go to 3, and we would have 6, right? So since all the we can't actually use division, this is actually difficult. Product of array except sum. So what if we used, no, that would be more than n squared times, that would be n squared time. So we must be able to do something in 2 passes. Maybe we can use space, right? If we use space, maybe we can trade space for time. So maybe if we have index 2 in the array, right, we know that this should equal index 8. This should equal 8, which will be 2 times 4 times 1. How can we create that problem? How can we create that? Well, if we take the sum, right, we'll do 1 times 2 times 3 times 4. We'll have 12. We should have 24, right? So we have 24, and let's say we want to exclude index 3. We divide by 3. We'd say 24 divided by 3. Well, if we do 24 divided by 3, we get 8. If we do 24 divided by 4, we get 6. 24 divided by 2, we get 12, and 24 divided by 1, we get 1. We're not allowed to use division. So maybe we did 24 modulo 6. If we do 24 modulo 6, we get 0. So we can't use division either. That is troublesome. So we can't use division. We can't use more than n time. So nums equals, interesting. So maybe there is some number magic we can use. So if we have 3, let's just say we go halfway through, right? Well, let's just say how we cut the array in half and see if that helps us do anything. So I have 1 and 2. So I have 1 and 2, right? And our answer is supposed to be 12 and 24. Can't divide. What's remaining is 3 and 4. So this doesn't work either. A multiplication is also just repeated addition. So maybe we can do the same there. Maybe we can do, if we have 4, right? If we have the output array, output value, which is this multiplication of all of them, it would be 24, right? If we have 24, right? What if we just implemented division? We could say, I mean, that is a little bit roundabout, right? But what if we just implement division with addition? Are we guaranteed that nums is always an integer? So it's always an integer array. So if that's the case, then we could do what we went originally, right, which was iterate through array and calculate product. If we calculate the product, right, we'll get 24, right? Once we have const product, once we have the product, right, we want to create our output array, and we'll have our product. What we'll want to do is to do another linear iteration. So we'll start at 24, and we'll say, how many times can we add our particular number to 1 before we get 24? So let's try that. And this would be linear time, so let's try and calculate the product. We'll say num of nums, right, and we'll say let product equals 1, and then we'll say product start equal num. Product should be 24, right, and then we can iterate, right, for const num of nums again, right, and what we'll push, right, is we'll do our own version of a division, right, and we'll say output dot push, right, helper, right, and we'll just pass in our product, right, and our particular number. And then from here, I think we should be able to just return output. So what if we try and implement that helper function, which is just going to do division by addition. So we'll take a product, which is going to be a number, right, and our num, which is just going to be a number, and we're going to return a number. And we're going to say let I equal 0, right, and we're going to say while I is less than, right, product, right, we're going to do I plus equal num, right, and at the end we'll return I. So we should be able to add, right, 1, 2, 3, 4, 5, all the way up to 24, and then we can place 24 in there. So if we run this, let's see if this makes sense. So our values that we get, our output was 24, 24, 24. So our product is 24, and we output dot push helper, right, and product and num. So helper is product is 24 and num is 1. So that should be 24. Then when we pass in 2, right, how many times can we add 2? Oh, and that's our problem, right? We need 2 variables actually. We'll say CT equals 0, and we'll say let value equals 0. So while value is less than product, right, we're going to do value plus equal num, right, but CT plus equal 1, and then we can return CT. So maybe we ran out of time for this. Our answer is wrong. So we do good here, right? There's nothing we can add for each number to get 0, but our sum here, or our product, is going to be a particular value. It's going to be -1 times 1 is -1, right, times -3 is +3 times 3 is going to be 9, right? And no matter how much we add for this particular 0, for a particular zero value, if we try to add for a particular zero value, so if num is 0, right, I'm actually surprised that this somehow gets to the end. This should be time limit exceeded. The number that we're adding to is going to be 0, right? We're saying, well, 0 is less than 6, so this should be time limit exceeded. But somehow it's not. Let's try running this one specifically. Somehow we're getting 0. Let's see what our product was. So our product was 0, okay, which is interesting because we're doing 1 times -1 is -1, odd times 0. I see. So we notice, right, with zeros, we're kind of going to want to ignore them from the output, right? And we're going to say times equal num, right, if num does not equal 0, right, or equal num, otherwise do 1. All right, so now our new sum should actually be the correct value, and we should get time limit exceeded. Since we're getting time limit exceeded now, what should happen is between 21 and 23, unless if num equals 0, right, and num, right, so that's perfect. If num equals 0, right, and there's nothing that we can add, right, to there's nothing we can add, right, which means if num equals 0, then the number that goes here is actually just going to be, so say if num equals 0, right, then we'll do output dot push the product. Else we want to do what we did earlier. So we'll run it for this case. So our time limit is still exceeded. We actually have a similar case for the other ones, right? Product is 9. There's no way you can keep working with -1 to actually get 9, right? So maybe what we can do, right, in the case where our product is actually 9, right, and our number is -1, maybe we just take, if we take the absolute value of both, then we actually get 9, right? And we don't want that value, right, because 9 divided by -1, or 1 times -3 is -3, times 3 should be 9. Should be -9 actually. So this version doesn't particularly work. But if we could do division, then we could say -0, or we could say -1 divide, well, we can't divide by 0. We could say 9, oh no, we could say 9, right, divided by -1. 9 goes into -1. -9 times. So our intuition for this is incorrect, at least depending on our sum. So the product accepts self in linear time. So what we could do if we traded space for time, what if we do something like this, where for each array, right, we'll try to create a map, right, where, well, that wouldn't be linear time, but it wouldn't be linear time. What if we try to create a map where for a particular index, like index 2, right, index 2, which would be actually be this 3 here, what's stored, right, is actually this 2 values, right, and these 2 values, right, would be 2 and 4, and the solution would be 2 times 2, which is 4 times 4, no, the answer would be 2 times 4, which is 8, which is just the numbers at those values. So to do that, we could iterate through the array, and maybe when we start at 1, right, we'll go to 2, and then we'll say, hey, the left-hand value for 2 is actually going to be 1, and then we'll go to 3 and right, so at 1 we'll say the left-hand value for 1 is not going to be anything, but at 2 we'll say the right-hand value for 1 we could do it 2 ways. We could do forwards and backwards. Maybe we could say, if we go forwards, right, we'll say that if we go for 2, we'll say the left-hand value for 2 is going to be 1, right, and then for 3, basically we want a map with the left and right hand side split up. But if we iterate through the array, we really only have access to values we've handled before. So if we iterate through, the only thing we can say is that the left hand value for 4 is going to be 6. And if we do it the other way, we can say that the right hand value is going to be 4 times 3 is 12 times 2 is 24. That would be 24 and 6, which would be the first and last elements. Now if we have the first and last elements, maybe we can do with the first and last elements, iterate through array and calculate the product. How could we iterate through the array and calculate? So let's try rethinking this. So we've already tried with the map and the linear time solution. Maybe there's another version of this that we can try. So since you have to do the sum, I don't think there's very many tricks you can do. Right, this 0 case throws a wrench in a lot of, I think, tricks you could have used to solve this problem. So I think whatever we do, we need some reference. We have to use some sort of space. And the space that we use is going to be required for negative, right, to actually get the sum. So how could we go about solving this in a way that makes sense? There's no hints. So this is interesting. If -1, 1, 0, -3, and 3. So you have 0, 0, 9, 0, 0. And they're saying the product of any prefix or suffix of nums is guaranteed to fit. So what if we calculate the product, right? If we calculate the product and then go in reverse, so we'd have 24, right? Then we could go down, right, and exclude 24, this index, right? How would you get 24 from 6? Let's see how many times it adds up, which we tried to do earlier with helper, right? maybe we were onto something with helper and it just requires some reconfiguring. But this doesn't exactly work because our helper function assumes that the sign of the number will not change depending on the sum. And the fact that the numbers can be signed or unsigned in the array kind of destroys that premise. So they said we can use divide. What if we use modulus? That probably doesn't help either. Can we visualize this as a 1, 2, 3, 4? Can we visualize this another way? What if we iterated from both sides of the array at the same time? From that point, we would have 1 and 4, right? And then we would have the inner arrays. So if we had 1 and 4, we'd always have access to the sum minus, maybe we would always have access to the sum minus value. So we'd have 1 and 4, right? Access to both of these, right? And we would say the value of this index minus the current index, right, would be 1 times 4 times 3, right? That doesn't exactly work. Array prefix sum. So you'd have 1 and 2. So if we did 1 times 2, we'd get 2. If we did 2 times 3, we'd get 6. If we did 3 times 2, we'd get 6. We know that any values which are equal, so maybe there's some specific magic. We know that any values which are equal to 1 can be replaced with the product, right? They can be replaced with the product. So about other values. So we have 1, 2, 3, and 4, but our output is 24, 12, 8, and 6. 0, 1, 2, 3. So maybe there is some magic we can use. What if we use the difference of the numbers as something? We'd have 1, 1. The no division part really gets me. Without using the division operation. So what if we took a Is there anything else we can glean from the problem description? Given an integer array nums, return an array answer such that answer sub I is equal to the product of all the elements of nums except nums sub I. The product of any prefix or sum of nums is guaranteed to fit. So maybe we can save, maybe we can save time if we save all of our pre-computed values. So if we're iterating through, right, we'll have 1, 2, 3, and 4, right? If we iterate to 4, we'll know that 1, indexes 0 and 1, right, give us values 3. Indexes 0 and 1 give 0 and 1, right, give us a value of 2, right? Indexes 0 through 3 give us the value of 6. So maybe we can use that to our advantage, and we'll use these intervals to represent values that we can skip or reuse. So if we do a value, so if we do 1 times 2, right, we know the sum of 0 and 1 is 2, and then we could do 1 times 2, we could do 2 times 3, right? We know that the range 1 to 2 gives us 6, right? And then if we do 4, right, we know the range that we're looking for is 0 through 3, and so we could check if the range that we have is 0 through 3, 0 through 2 is in the map, and if it isn't, then we'll just break it down, right? We'll say, okay, well, do we have anything going from 0 going to anything less than that range? And if we don't, then maybe so I kind of want to think that maybe we can reuse intervals. We'll have 24, 12, 8, and 6 though. So let's run with this interval idea. So maybe we'll have 0 to 1, right, gives us 2, right? Maybe it'll be inclusive, right? 0 to 2, right, gives you 6. 0 through 3, right, should give you 24. Zero to 2, so 0, 1, 2 give you 6. 0, 1, 2, 3, right? Would be 2 times 3 is 6, times 4 is 12. So maybe, right, we could do another linear iteration through, right? And let's just say we need to get a value for index 2. Right, if we know we want to get a value for index 2, we'll check if 0, 2 is in the map. It is, we can return 6. Or 0, 1, 2, right? Maybe it is exclusive. So we do 0 to 2, 0, 1, and 2, right? That would give you, we want the product minus this, we want the product minus this number. So we'd say for index 2 that we want, right, which would actually be, so the index so we want to do this for the number 2, right, which is actually index 1, right, which means the range we're supposed to generate, right, would actually be 0, right, times 2 to 3. We don't have 2 to 3, right? Since we don't have 2 to 3, we'd have 0 through 1 equals 2, and then 2 to 3, we can just do this number times the current number. From the looks of it, this seems like a simple enough problem to solve in linear time and space. We can simply take the product of all elements in the given array, and then for each element x of I, we can simply find the product of array x of self I by dividing product by x. Doing this for each element would solve the problem. However, there's a note in the problem which says that we're not allowed to use a division operation. This makes solving this problem a bit harder. It's It's much easier to build an intuition for solving this problem without division once you visualize how the different products of self look like for each of the elements. Let's take a look at an example array and the different products. So the input array looking at the figure about how we can figure another way of computing those. Looking at the figure about we can figure another way of computing those different product values. Instead of dividing the product of all the numbers in the array by the number at a given index to get the corresponding product, you can make use of the product of all the numbers to the left and the numbers to the right of the index. Oh, that's what we were going for. Multiplying these two individual products would give us the desired result as well. For every given index I, we'll make use of the product of all the numbers to the left of it and multiply by the product of all the numbers to the right. This will give us the product of all the numbers except the one at the given index I. So they use the product of the elements to the left. So products of the elements to the left. So if we do 1 input array and then we do 2. No, actually they're just doing and they'd fill up the numbers up. L sub I times R sub I, return the answer. This would be linear time, where n represents the number of elements in the input array. We use one iteration to construct the array L, one to construct the array R, and one last to construct the answer array using L and R. Interesting. That's unfortunate. Yeah, we had the intuition for that, but we couldn't get to the goal answer. That is unfortunate. So given the root of a binary tree, determine if it is a valid binary search tree. Valid BST is defined as follows. The left subtree of a node contains only nodes with keys less than the node's key. The right subtree of a node contains only nodes with keys greater than the node's key. Both the left and right subtrees must also be binary search trees. So 1 should be less than 2 and 3 should be greater than 2. So 1 should be less than 5. Oh, and 4 should be greater than 5. So this is interesting. I think this is interesting. Nodes in the tree is 1 to 10 to the 4, so we know we have at least one node, right? And I think the goal solution of here would likely use recursion. And let's just say we had 2, right? We want to make sure that 1 and 3, 1 is less than 2, right? And 3 is greater than 2, right? And then from there, we'd want to make sure the same of that for their subtrees, right? Unless their children were null, right? And so I think maybe we could implement a version of that with return helper, right, of root, right? And the function helper is going to take a node, which is a tree node, right, which we know can't be null because of the problem solution. And we're going to just do some checks. We're going to say, hey, if the node exists, right, then we want to do some work, right? But what if the node doesn't exist, right? So if the node doesn't exist, right, then we actually will just return true as well. But if the node does exist, right, then what we want to do is make sure that right, we'll say left, right? So we'll say if node, right, dot left, right? So if that left node exists, right? If that left node exists, right, and node.val, which is 2, right, is greater than node.left.val, then that's okay. So it's when node.val, right, is less than. So if this node 2 is less than this node 1, right, then we would have a problem, right? So we return false, and we want to duplicate this as well, except for node.right. We change the rules a little bit, right? We want to say if node.val, right, if 2, right, is greater, if 2 is greater than our value, right? So right now 2, right, so 3 should be greater than 2, but if 2 is greater than 3, that's a problem, right? So you want to return false, right? If we make it through both those checks and we're okay, right, then we want to also call helper for node.left. Geez, I'm pretty sick. Helper for node.left and helper for node.right. And the way you want to actually string this together, right, is you want to say true for this current node, right, and helper, right, and for these two first trees as well. So we'll start with root, right? We'll say 2, right? Does left node exist? Yes. Is node.val, which is 2, less than 1? No. So right exists. Is node.val 2 greater than 3? No, right? So we return true and helper node.left and right. When we go to 1, right, we check if the node exists, and it does, right? And neither of the nodes exist, right? And so we're going to return true and helper.left and right, but none of them exist. We return true, and return true, so we're good. So I think we can try this. So in this case, they like us to return false. So is 2, we actually return true. So interesting. So we know our node 2 exists, right? We're going to say, does our node left exist? Yes. Is 2 less than 2? No. So we should return false, but we don't. And then we say, okay, does the right node exist? It does. And is node greater than 2? No. So we should return false. So that is actually interesting. I'm wondering why we're returning true here. So we're returning true. Where we go in, node.left exists, node.val is less than, oh, right, if it's less than or equal, right, and if it's greater than or equal to, then we'd like it to return false. Interesting. So we have 5, 4, 6. So here we're returning true, and they want us to return false. So it looks like the tree we have is actually 5, right? 4, 6, right? We have null, null, and 3 and 7. So, oh, right, all the way down. Okay, so this is actually way more difficult than I thought. We're only checking on a node by node basis. But it's actually more complicated than that, actually. That is interesting. So this is actually not a simple problem. So right now, our original solution was taking linear time to visit every node, but now we want to visit nodes 3 and 7, well, nodes 8 and 3, and make sure that it's also less than its parent still. But still, they could give us a tree, right, where 3 is, it's 3, right? Or 7 has a child, right, and its value is actually 3. So we want to make sure that each value is actually less than our original value. So maybe we could keep a rolling minimum, right? And we'll have to say, okay, oh yeah, rolling minimum that you have to be greater than, right? So if we do that, we'll have 5 and 8, right? And we'll go and say, hey, is 5 great? 3 is not greater than the minimum value. And in that sense, minimum value will be dependent on the current subtree that you're in. So this could actually work if we keep a rolling minimum. Let's try for a slightly more complicated case, right? Or maybe we would have something like 2, right? Our rolling minimum, right, would have to have been the current node, right? And it only works for current nodes, I believe, right? We'd have 5, 8, and actually 7 also breaks the rule, so let's have 9, right? And 9 would still fit, right? But our minimum that you need to be greater than is at least 5. Right, if you're not at least greater than 5, then it's a problem. But what if you're greater than 5? Okay, so let's say this equals 6. Well, even if you're greater than 5, right, you still have to be greater than 9. So I think what we're noticing here is that we want to keep our minimum, our rolling minimum, but at the same time, we're going to keep our validation structure that we have now. So we should just have to add our rolling minimum and our lowest so far, right, is going to be a number. This number, right, we're going to pass it, and it's going to start at root.val. All right, so we're going to go in, right, with 5. We're going to say, hey, right, we're going to say, hey, it's 5. And maybe we can actually skip it. We can just do helper and helper. Actually, no, because we want to make sure. So if you start at 5, right, we're going to say, so we're going to say is 5, right, is 4 less than 5 if node.val, right, oh yeah, if 5 is less than 4, that's a problem, right? But at the same time, right, we want to make sure that node.leftVal is also, let's say, and node val is less than or equal to node left val, or node.left.val, or we'll say that lowest, right, which is 5, right, or lowest, which is 5, is less than or equal to node.left.val. So is 5 less than or equal to 4? No, so we're good, right? And then we'll say is 5 greater than or equal to 8, right? No, so we'll add the same thing here. Node.right.val. And so if 5 is greater than or equal to 8, if 5 is greater than or equal to 8, that's also a problem. So then we'll be at 4, right? And we're always going to want to min, right, helper, the lowest value we pass in, right, is always going to be the math dot min of lowest, right, or node dot val. Dot min of lowest or node dot val. And so here now we have a bit more going on. So for this tree, we can say 5, 4, and 8, right, will be good when we get to 4. We're going to say our lowest so far is 4, right? We're going to say, hey, is 4 less than or equal to node.left.val? Well, the node.left doesn't exist, node.right doesn't exist. So we're going to return true and helper for both, but they don't exist, so we return true. We're going to go to 8, right? True and helper node dot right. We're going to go to 8, so we're going to have be an 8, right? Left and right do exist. We're going to say, does node left exist? It does. So is, oh, in the value we're going to pass in, right, it's going to be 5, the main of 5 or 8. Oh, it's going to be 5 or 8, which is going to be, no, it's going to be 5 or 5. And so we're going to be an 8, and we're going to say, hey, is our current node, right, is node.val, which is 8, less than or equal to node.left.val? No, right? But its lowest, which is 5, is 5 less than or equal to node.left. Is 5 less than or equal to node.left? No. This is actually not exactly what we want either. What we want is the ability for 8, right? 8 right here to check, or 3 right here, right, to check if lowest, right, is it less than or equal to 8, right? But is it also greater than the lowest so far? And I think that's what we always want to check, basically. So we're going to be an 8, right? We're going to say, hey, is lowest greater than or equal to left.val? Well, it is, right? 5 is greater than or equal to 3, right? Which means we want to return false. Well, let's just say we get to 9. We're going to say, okay, now we're going to check node.right. Node.right does exist. Is 9 greater than or equal to, oh, is 8 greater than or equal to 9? No. But is lowest, which is 5, is 5 greater than or equal to if our number is less than our lowest, that's a problem. So is our number is lowest, oh right. So if lowest, which is 5, is 5 greater than or equal to 8? No. Is 5 greater than or equal to 9? No. So this is good. So I actually think this does make sense, and let's copy, let's run it for this case to see if the code still works. And then I think if we use this case, we should be good. So we still have a false case where we have 2, 1, and 3, right? 1 is less than 2, and 3 is greater than 2. Our output is false. So that's interesting, right? And we mentioned this earlier, right? Because when you start with the root, is actually a sort of a small problem. So what we could do, right, we basically want to ignore the root node, so we don't want to do this lowest logic. So if we start at node 2, our root node, right, we're going to say, does node left exist? Yes. Right. Is 2 less than or equal to 1? No. But is our lowest so far, which is 2, greater than or equal to node left value? 2 is greater than or equal to 1. And so one way to quickly fix this is to do node and node right, if node and node is not equal root, and then we could pass in the root tree node to every call, and I don't think this is the best way to do it, actually. Basically, what we can do instead is do root.left with root.to start, right? We can say helper root.right with root.val. And the way we can string this together is check if the root makes sense, is we can just do a short version with here, right? And we'll also call and we can get a variable called root good, right? And we can check, right, if root, right, and can we guarantee that our root exists? We can always guarantee that our root exists, right? So we can say let root good equals false, right? And we'll say if root dot left, right, we'll just assume it's true, right? And we'll say, so say if root dot left exists, right, and its value is greater than or equal to root dot val, right, or if root dot right dot val exists and its value is less than or equal to root dot val, right, then set root good equals false. And so for this particular case, we should be able to get true. And I must have made a typo. So we're running into too many edge cases, which I think just means that I think we're trying to skip too many nodes. I think the reality is for every node, we'll have to make sure, if we take a given tree, 5, we have to make sure that if we take given, so this should be 6, right? We have to make sure that every node after that is greater than 6, right? And then every node right here is less than it, right? And so I think that's the easiest way to do it, or the most straightforward way, but this actually would give us like n to the n time. But I think one way we could do this would be to do a level order iteration, and then from here we can do a check basically, and we'll just say, hey, validate, right, this node, right? And what it's going to do is it's going to take this node and check that every node on this list is less than this node. So to do that, let's change our entire approach and we'll delete all the code so far. So we'll do a level order iteration with the queue, right? We'll let cur. So level order iteration with the queue, and we'll say while queue dot length does not equal 0, right? We're going to start the queue with root, right? We're going to say let cur equals queue dot shift. So we'll take one off the top, right? It's going to be 2, right? And then here we're going to say validate DST, right? And if we validate it, then we can do queue dot push, cur dot left, cur dot right. This whole left hand side, they're only going to want to do if cur actually exists. And so this should give us our level order. So we get 2, right? Do something to 2, push 1 and 3 on, right? Pop the next one off, something 1, push null and null on, right? Push null and null on, and so we should be good. And then from here, right, we can just create a function called validate. It's going to take a root node, right, or a node to start with, right, which can be null, right? It's going to take the value, which is going to be a number, right? It's going to return a Boolean, right? So if cur, right, otherwise we're going to return true if the value doesn't exist, right? But we can reuse some of the logic from earlier. We're going to make sure, right, that if cur dot left exists, right, and cur dot left, and it exists, we don't need to save navigation, cur left dot value, right, is actually greater. So cur dot left, which is 1, and 1 is actually greater than cur dot val. What we mean is greater than or equal to, right? We're going to want to return false. We can duplicate this, right? We're going to say if cur dot right exists, right, and cur dot right's value, right, is actually less than or equal to cur dot value, we want to return false. Otherwise, right, you want to return true and validate that it's less than a particular value, right? So we're actually going to pass in a node here for like 4. We want to make sure that every node here in this tree is greater than 5. Right, and so we're going to need we're going to say is right, which is going to be a Boolean, right? We're going to say if cur, right, and if right. We actually don't have to do this version. Actually, we can keep this, right, because we still need it anyway. So we have to validate the tree itself, like the substructure. We also want to make sure, right, that if right, then we want to do the similar things, right? We want to say, right, if we're going right, then we want to make sure that if cur.val is greater than, since we're going right, we want to make sure that every value is greater than value. If cur.right is less than or equal to value, right? And if cur dot left dot val, right, is less than or equal to value, right? Or cur dot right dot val is less than or equal to value, right? Then you also want to return false. We can actually fuse these. We can just say if right. So if right and cur dot value, right, is less, so we're passing in 2, right? Let's say we're passing in 5, right? We're saying if cur dot right, if right right? And cur dot value, right? If 4 is less than or equal to 5, that's bad, right? If 3 is less than or equal to 5, that's bad. If 6 is less than or equal to 5, that's bad, right? And then we can duplicate this. We can say, right, if not, and actually we don't need to see, if it's not right, then it must be left. But we'll just make this an else if not right, and we'll just copy it. So if not right, then it must be left. And we'll make sure that if cur's value, right, which is 1, is greater than, so we have 5 here, right? Let's just say, imagine the subtree is over here, we're going down here, right? We have 4. We're gonna say if the cur value is greater than or equal to value, then that is a problem. And then we want to validate the subtrees. So say cur dot left, right? And the value, next value that we want to work with, right, is going to be cur dot val. It's going to be false, right? And validate cur dot right, cur dot val, and true because we're going right. And so the solution we failed on, we'll keep this one here. We should get 2, 1, 3 should be good here. Oh, we didn't even validate the BST. I mean, we didn't call the start. So we'll say, if not validate cur, right, and the starting value so we're into a similar problem, except that problem is now being recreated everywhere. If we pass in cur to start, then the value itself is going to be a problem. And the value itself is going to be a problem, so we need a way to validate the main structure and if a subtree makes sense is kind of what we want to do here. So we'll validate the subtree, and then we'll call validate for the left and right nodes. So we'll say function validate, subtree, we'll say node, tree node, right, and it returns a boolean, and all we basically want to do is what we're doing here, right, and then otherwise return true. So we'll call it subtree valid, right, and we'll say if subtree invalid, right, we'll just pass in cur, we'll just return false. And basically what we're doing here is you want to make sure, right, before we validate the subtree, right, I'm going to say, hey, if subtree is valid, right, for cur, or if the subtree, right, if the subtree is valid, or if the subtree is invalid, right, or validate cur dot left, right, with cur dot val to start, or we don't validate cur.right. I mean, we validate cur.right, right, with cur.val, and we're going right, which is going to be true, and we have to pass in false, right. Then we basically want to say that we should return false. Otherwise, we want to keep going. So we're missing one more. We called it node up here, we just change it to curve for the sake of time. We're returning undefined. So if we make it through this whole thing, right, we'll return true. That's something I neglected. And so let's try for this test case, which we failed originally. So we're returning false when we should be good, because if the subtree is not valid, then we have to return false. 1 is less than 3, greater than 5, right? 0 is less than 1, 2 is greater than 1, right? And 4 is less than 5, and 6 is greater than 5. So maybe there is something else going on. So we pass in this left subtree, right? And that is going, so if we take cur, right, which is root, we're gonna take 3 off, validate that subtree makes sense, right? And then we're gonna call validate for the left, right? And the left is basically going to have 3, 1, 5, right? 0, 2, right? We have 4 and 6. And we have 0, 1, and 2 are less than 3, 3 less than 1, 1 is greater than 2, right? So if right, if cur.val, wait a second. We don't want this to be, oh no, we do want this to be else if. Passing in 3, right? Then we call validate for the left subtree, right? 1 does exist, right? And right is not false, right? It doesn't exist. So is cur.val, which is 1, is 1 greater than or equal to value, which is 3? No. Is 0 greater than or equal to value? No. Is 2 greater than equal to value? No. Is the subtree invalid? No. So we should be good. And then we call it for right, which is 5, right? And then we say, hey, is 4, call it for 5, and we'll say, are we going right? We are. So we're gonna say cur.val, which is 5, is 5 less than or equal to 3? No. Is 4 less than or equal to 3? No. Is 6 less than or equal to 3? No. Okay. Now we're gonna say, okay, is left and right do exist? Is 4 greater than or equal to 5? No. Is 6 less than or equal to 5? No. So I'm actually not exactly seeing where we're returning false. we made that tree and it is valid. So where in our code, so we're pushing off 3, pulling off 3, right? 3 does exist. Is the subtree valid? I mean, is 1 greater than or equal to 3? No. Is 5 less than or equal to 3? No. So we return true. We validate left subtree, which is going to be 1. So now we're at 1. 1 does exist. We're at else if, right? So cur.val, right? So now we're at 1, right, with validate, cur.left, right, with 3, right? And now we're gonna say is 1 greater than or equal to 3? No. Is 0 greater than or equal to 3? No. Is 2 greater than or equal to 3? No. And is our subtree invalid? No. We return true and validate left, right, with 1. Now we're in 0. 0 does exist, and left is 0. And left, so we're saying we're at 0 with value equals 1, right? Is 0 greater than or equal to 1? No. Right? It's correct. Doesn't exist, right? No. Is our subtree valid? Right? So we're at 0. We say if cur left exists, it doesn't. Cur right doesn't exist. We return true. Then you return true with cur left, and neither of them exist, so we return false. I mean, neither of them exist, so we return true. Let's print cur.val when we return false. We return false, cur.val is 3. So which one of these was true? Is our subtree invalid? Well, we can is our subtree valid for cur? We should get that it is valid. Okay, what if we validate cur.left, cur.val, right? And we're false because we're going left. So we're returning false. What about for validate cur.right, cur.val, true? Are we also returning false for that? Something's wrong with our validation here. So we know it's when we're at node 3, so it's right at the top, right? And here we say subtree valid, right? If our subtree is invalid with node equals 3, right? Let's check that code. Does cur.left exist? No. So since none of it exists, left or right, well, left or right does exist, right? So we're gonna say is 1 greater than or equal to 3? No. Is 5 greater than or equal to 3? No. No, it's 5. It's 5 less than or equal to 3? No. Now, is 1 greater than or equal to 3? No. So it can't be here. Maybe it's here. So if right, so if cur.val, which is 1, right, is 1 less than or equal to 3, it's good. What I think we want is if it's greater than or equal to the value, then that would be a problem. So we basically want to swap these. Wait, so we're still false? So we're saying cur.val, which would be 1, is 1 greater than or equal to 3. Then is 0 greater than or equal to 3? Is 2 greater than or equal to 3? No. And then we're saying, okay, now we're going right. Right is 5 less than or equal to 3? That would be a problem, right? Is 4 less than or equal to 3? 6 less than or equal to 3? No, so none of that is true. So maybe it's in a deeper subtree, right? We pass in 1, and then we go down to 0, and we say, okay, is 0 great? But yeah, we're just validating that it makes sense. This is bad, but I just need to know which one is causing me this error. So we're just going to know here. It's actually two twos and 1 1. So here I need to know what cur.val is and value, and here I need to know what cur.val is and value. So cur here is 1, and we said is 1 greater than or equal to 3? No. And then no, we're looking at 2, so we're saying is cur, which is 1 less than or equal to 3. Oh my god, I just realized this is a duplicated line with, oh no. This should be if cur.val. So we're saying if 1 is less than 3, we're supposed to be going right. Which means our cases are flipped. I had if not right here, which is also a problem. So now this is making more sense. So if cur.val, which is 1, right, if 1, no, right, 2 is saying 1 and 3. So cur is actually 1, value is 3. So cur is 1. Wait, if not right. basically, if we're going right, we want to check, if we're going right hand side, we want to check if the value itself is less than or equal to the number. If that's the case, we'd have this value here. So it'd be swooped back to the way it was. So if we're going right, and cur dot value, which is 1, is less than or equal to 3, doesn't make sense though, because why would we have 1? Why would we have access to 1 and 3? Basically saying not right. So if we're not right, then it must be going to cur dot left. When we're going left, we actually have access to 5. Cur is actually 5. Let's just say we call validate right with false. That would mean that we're not, so not right? If we're going right, then we want to say if right exists. If we're going right, cur dot val, we're going right. If we're going right, so we're going to 5, right? When is our problem state? It's if the right hand node, which is 5, is less than or equal to value. So actually this still is fine, I think. But if we're going right, it's our goal case, our problem case is when 5 is less than or equal to value. So if 5 is less than or equal to value, right? If our left value, which is 4, is less than or equal to the value, which is 3, and our right value is less than or equal to the value. Similarly, if we're at 1, our problem case is when our current value is greater than or equal to the value, right? Our left value is greater than or equal to the value. Our right value is greater than or equal to the value. So we shouldn't have to swap anymore. This should give us the correct answer. Then when we call it again, right, we'd want to make sure that all of our current values maybe this is the problem right here. We actually want it to be value all the way down. Call it 1, right? We're going to say, okay, we're going left for this. We want to make sure that 0 is less than or equal to All right, if 0 is greater than or equal to 3, then that's a problem, right? Right, but then we go to the right-hand side. So I think I'm seeing the problem now. We don't want to put in new values. I think we just want to propagate right and left values depending on our original call. We're still false. So we call it with false originally, which means that anytime, right, we go right, then we want to make sure that value is doing good. So if we validated and it's good, so if it's not good, so it's not validated. I feel like I'm so close on this one. Cur dot left and cur dot right. Now we just need to follow it more closely. We just need a smaller example to see exactly what's going on here. Let's just say we have, does our current code even work on the smallest version here? Does. What about something slightly larger? Okay, it does. This is a problem. So for case we're specifically failing on is 3150246. What is it about this case that is problematic? So you have 3, 1, 5, 0, 2, 4, and 6. Where are we returning false here? So we're going to push 5 into the queue, pop it off, validate the subtree. That the subtree does make sense. Then we're going to do left, validate with left, which is going to be 1, with false equaling right equaling false. Then we're going to be in here, 1 does exist, and we're not right, so cur.val, and value is also going to be cur.val, which is 3, right? And so we're going to make sure, right, that every node in this left subtree is not greater than or equal to value. So we're going to say cur.val, right, which is 1, is 1 greater than or equal to 3? No. Is 0 greater than or equal to 3? No. Is 2 greater than or equal to 3? No. Right? And our subtree is still valid, but let's check anyway. Is 0 greater than or equal to 1? No. Is 2 less than or equal to 1? No. So we return true. Then we do validate of left, right, which is going to be 0, right, and our value is still going to be 3. So we're going to say if cur, so 0 does exist, and we're still going left, right, and we're going to say, hey, is 0 greater than or equal to value? No. Is value is undefined greater than equal to value? No. Right? Is the subtree valid? Right? This should return true. So we're good. And then we go left, right, with value, and then cur doesn't exist, we return true, and this we return true. Then we go back up to 1, right, and we do validate right, but with false still, right, and we're going to say is 2 greater than or equal to 3? No. I wonder if they have a debugger in this. thought there used to be. Yeah, this is one of those things where I'm not exactly certain why I'm not getting the correct answer. The solution that seems to be the problem is, so you have 5, right? And then we reduce 1, 4, 5, and that's not exactly our problem. Our problem is this test case. So we print 3. So let's just print the remaining values. We'll do cur left val cur. So we're basically at 1, 0, 2. So we're at 1, 0, 2, and okay, we're in the second value. Wait, we can't go right. So somehow we're in this 2, right? But we actually can't go right from there. So there's no way that we can be in. Once we get a right value, we propagate it throughout the whole thing. But we're in here, we're at the node 1, 0, 2 with right equals, there's no way. And we'll print right as well. So right is false. So how is right false? How is right false? Wait a second. No. Oh, no way. Is it really a parenthesis difference? So what I was really deep, so I understanding was correct. It was literally that. That's so strange though, because I'm certain I've used right and so I needed to parenthesize my expression. That is strange. Wow, that is unfortunate. That means we solved this problem a very, very long time ago. That's very unfortunate. This makes me wonder though, how much of this did I really need? So I have to try a slimmed down solution in the future. This approach would even work for some trees. The problem is this approach would not work for all cases. Not only the right child should be larger than the node, but all elements in the right tree. Here is an example. At each node, the conditions node.right.val is greater than node.val, and node.left.val is less than node.val. But it's not BST because not all elements in the right tree is larger than 5, which is facts. 4 is not larger than 5. Recursive traversal with valid range. The idea above can be implemented as a recursion. One compares the node value with its upper and lower limits if they are available, then repeats the same step recursively for left and right subtrees. This is a very eloquent solution. If not node, return true. Otherwise, the current node's values must be between low and high. Node.val is less than or equal to low, or node.val is greater than or equal to high. Then left and right subtree must also be valid. Alright, so we need to understand this one because this one is very, very straightforward. So BST and not BST equal not BST, return false. So is BST lower limit equals none, upper limit equals none, limits not available, check right and left subtrees. Is left subtree BST, lower limit equals none, upper limit equals 5. 1 is less than 5 and no child nodes, yes it's BST. So right tree BST, lower limit equals 5, upper limit equals none. 4 is less than 5, it's not BST. So if the node doesn't exist, return true. If the node's value is less than or equal to low, alright, so if the node's value is less than or equal to low, or node value is greater than or equal to high, then it's a problem. The left and right subtree must also be valid. So the new low for every subtree is the current node's value. And what we return is validate root. So we could have definitely had a much simpler solution, which we will attempt another time. But there's 20 minutes left, so let's try. Rotting oranges. So you're given an M by N grid where each cell can have one of 3 values. Actually,